All right, line C4, learning task number 3, describe the use of power quality analyzers. This is not something that you're going to learn from an old journeyman at your job site, because a lot of them have not dealt with a lot of this, because a lot of our power quality issues really started coming about from the 2000s and onwards, once we started to go and see a lot of changes in technology, particularly in the advent of variable frequency drives that were starting to gain popularity all over the place, as well as a lot more computerization, LED lighting, and electronic ballasting of stuff. As a result, it's something that had to go and be a fairly recent and a fairly rapid development that was going to take place. For a number of years, there was really no standard. Then after a while, the IEC 61000 4-30 Class A standard was adopted. And it's a standard that talks about what a power quality analyzer should be able to go and do, what sort of parameters it needs to have, for sampling rates, repeatability, export of data, things like that, that all are going to be placed inside of it. So when you buy yourself a power quality analyzer, as long as it's compliant with that, you're going to be getting something that will be able to do the bulk of the work for you. You just need to go and put these things in. And you have to put them in properly. Like any other tool, if you misapply it, it's not going to do much for you. We're going to go and have a couple of different things that we can do. We're going to go and have instant analysis as well as logging that we're going to be able to do. Instant analysis, where we're going to take a look at the job right in front of us. Long-term logging is going to be where we've got some sort of an issue. It might be hard to track down, or maybe we just want to get a good baseline so we can sort out how to go and size, some power factor correction, if it's going to be lagging bars, or maybe for, any other type of filtering, harmonics, etc. But we just want to take a longer reading out of something. And then a power quality logger is going to go and log that for us. Let's start with our simple ones. Our simple ones are going to give us an instantaneous, this is what's happening on the system right now, and it's going to be a power quality clamp-on. Power quality clamp-ons are going to be limited in the number of connections that we are going to be able to make at any given time. This is designed to go and be placed around a single conductor that we are going to have. And at the same time, we're going to go and have two jacks down here on the bottom that are designed to go and measure voltage, usually voltage over to ground. So one of these is going to go and measure voltage on the line. The other one's going to go down to ground off of there. And then we're going to have our line itself that's going to go through. It's going to tell us exactly what's happening on that phase. And we can't go multiple phases with this because we've only got a single jaw, right? If we run multiple phases through the same window, the fluxes are going to cancel each other out. So we'll use this for a line-by-line analysis. Great for, small and medium-sized companies because it's still a pretty powerful tool. You can still do stuff one at a time, but it's not going to go and give us the same sort of instantaneous holistic view that we would get out of some of our larger power quality loggers. You are going to be able to do things like measure your peak inrush currents. You're going to be able to take a look at peak voltages, and you're going to be able to go and display what is being shown, or display what you've actually got. Over here, we're seeing that we have got voltage that looks pretty consistent, so I don't think I've got a voltage problem off of this one, because when I analyze that, it tells me that this thing is going up and down properly. It's only 12 volts off of this one, but that's okay. The AC system looks fine. What I am seeing is that I am going and having just a really rapid boom, and a boom, and a boom, where I'm pulling current out off of each of these, which tells me that I'm looking at a non-linear load. Really, the definition of linear load versus non-linear load is whether or not there is a direct relationship between my voltage and my current at all times. A linear-looking current would be following the same path as my voltage. In this case, we can see that the voltage pathway and the current path are completely different, so it's going to be a non-linear. That's great. It's going to be, be able to show us that we're getting spikes. We can sometimes go and tie those spikes back to actual pieces of equipment that are going to be out there, but there's more useful data than that. One of the big things that you're going to go and get is going to go and be your THD that I'm going to go and have. THD is going to stand for total harmonic distortion that I am going to go and have. And what it's going to do is it's going to go and tell me which of my individual components are being disturbed, or basically where my junk on the system is coming from. if you're having problems with motors overheating, it could be that we have got zero sequence. That would be a neutral thing, but that would be uncommon for us to necessarily have motor problems. It's more common that for the motors, we're looking at either we're going to go and have positive rotation, or that we're going to have negative rotation that's going to be counteracted. And so when you take something like this, this is going to allow you to go and see which of your individual harmonics are going to be spiking at any given time, and those spikes can tell you which areas you're really struggling with. Over here, we're seeing that the closer we are to our fundamental frequency, the higher the spikes that we're going to be, and we're attenuating as we're getting further and further away. We should see roughly the same thing on our voltage as we get closer over here on our initial one. Then everything else past that is going to be dropping away a little bit further. This one shows that we have got on our first order, we got, that's going to be 0 over here, that we've got regular voltage, that's our ratio, but then we're seeing on our second order over here that we are then seeing this massive spike. So I'm going to go and have, counter torquing, etc. These numbers across the bottom on this one don't line up. Don't worry too much about, over analyzing this graph. The whole point is that it's going to go and show you where these things go and break down on there. There usually is methods where you can go and hook these things up and take a short time reading, put it onto a wall wart so that it's going to be plugged up or plugged on and not running off a battery, and then that you can log onto like a USB or something. But they're going to be limited in what they can go and capture. Plus, these ones are only going to be capturing a single line at a time. A power quality logger or recorder is going to go and give you much more information. If you take a look at this over here, you see that this thing has got, well, it's kind of hard to see on the drawing over here, but it's got a whole pile of jacks that are going to go into the top over here. These jacks are going to go and be associated with 4 of these current loops. Each of these loops here, you're able to unplug them from one of these. You can wrap them around a line and then plug them back in. So I've got 4, which means I'm going to be able to go and log A phase, B phase, C phase, as well as my neutral for current with these. And then I'm going to go and have an additional, you can't really see them off of here, but an additional set of voltage probes. So I can go and connect over each of my lines, my neutral, and my ground itself. And then this is going to go and capture all the lines at the same time. I'm able to go and do some things. If you take a look at that picture that's in the middle there, you can see that this is going to go and be vector values. They're at 120 degrees apart, and I'm actually going to be able to take a look at where my voltages are, where my resultant currents are going to be, any lead or lag, any voltage or current imbalances are going to be really easy to see off of that. Plus, I will have other screens, similar to these, where I can just pull out my THD. Power loggers versus power quality recorders are a slight difference, but it's not a huge one. Really just the big difference between them is just going to be the number of readings that they're going to go and take, the size of memory that they have, and how quickly they can process multiple points of data. My power loggers are just going to go and grab, point, all like the voltages, then all the currents. They're just going to cycle through that, grabbing individual points. Whereas these are going to be simultaneously grabbing all voltages, all currents at the same time, storing them. And you're going to be able to store them, based upon the millisecond or things like that, which are going to give you a lot more data than what you have off of your power qualities, which are going to be much further spaced apart. You can go and take with the power quality, you can say, I want to go and get a voltage every minute. And so you got a long runtime. You can leave that thing going for a week. You're going to take a voltage and a current reading every minute, but you're not going to see transients or surges or things like that. You're just going to see the overall system, how it's, being used. Power quality loggers, generally more so going to be used for doing things like I'm going to add on to a service. And so I've got to go and figure out how much room I have, or, can I actually add this expansion to the plant, etc., where we're looking for just coarse data. If it's going to be something that we need to catch what the culprit is, you're going to have to go with the power quality logger, power quality recorder, which is going to go and give you just fine detail inside of there. So all of the data that you're going to get out of these can be exported, whether you're looking at a logger or at a recorder. If it's a modern one, you're going to be able to go and export these as files onto a USB, where you can then go and run them through, there's going to be multiple programs and analysis software that is going to come direct from the manufacturer. And a lot of that is just going to be able to walk you right through. It's going to take the raw data in, and then you're going to go and walk through the software package with that data, and it's going to say, okay, do this, do this. And then, seeing from all this, we would say that your biggest problem is this, and, your best way to go and mitigate that is to do X, Y, or Z, etc. Power qualities analyzers are going to go and give you waveforms similar to what we saw off of the clamp-on one. You're going to be able to go and display either single phases at a time, just the volts that you're going to go and have here plus the current, or you're going to be able to go and take these things and see multiples at the same time. A lot of them also allow you to go and superimpose your values of voltage, your values of current, so that you can see if there's going to be any values of voltage or current that are going to be out of line with each other. They also allow us, by seeing both of these at the same time, allow us to go and differentiate when we're dealing with linear versus non-linear types of loads. Non-linear loads are going to be where it's not following the exact same waveform as my voltage, and we see that over here. These are going to be non-linear loads based upon the way that those waveforms look. Transient waveform capture can be set up inside of these. That's going to be where I'm going to use triggering. Triggering is basically where you're going to go and set a threshold. And you're going to say, hey, look, if I end up with anything that rises more than 5 volts above where I should be, I want to go and have that recorded. Or if it happens faster than this or whatever, you can set times, you can set current levels, voltage levels, etc. And then what it's going to do is it's going to save those into a special file so that if you've got some sort of transients you're trying to capture, it's going to go and pull those out so you don't need to scan through, hours and hours of data. Once you have taken your metering, placed the metering on, and figured out, what you've got for distortion and where you have got harmonics, but specifically, the types of harmonics that you have and their frequency that they're going to be operating at, you're then going to be able to start to apply some of your corrective actions. Corrective action is going to go and start on the installation itself with the physical sizing of the installation itself. Make sure your grounding and bonding are going to be done correctly. Make sure that your bond size is going to be significantly large enough it can deliver fault current back to a neutral. And then make sure that your phase conductors, if you got a lot of non-linear loads, make sure those phase conductors are going to be larger. That you're going to go and have dedicated feeder cables where necessary so that you don't share harmonics. It's better to run out, if you've got a huge VFD, it's better to go and run out a separate cable for that rather than go into like a small sub-electrical room and feeding a bunch of other stuff off of it. Make sure your neutrals are going to be large enough. Make sure that when you are dealing with conduits that you're not just relying on the conduits themselves to necessarily carry all of that bond current back. Okay, make sure you put the insulated bond conductors inside, etc. If you are still having issues past the original installation where you're oversizing and your pre-building didn't work, then what you're going to do is you're going to take a look at power conditioners. Power conditioners are going to be placed at your main service, and in a lot of cases your power conditioners, when they're a second, are going to go and just try to snub anything before it either gets in from the outside or before we send anything back out to the outside. Transient voltage surge suppression is going to go and filter, spikes that come in from the outside generally. We don't have a lot of spikes we generate ourselves. Noise filters are going to go and filter stuff that we have inside so it doesn't go out and, cause problems anywhere else. Once again, these are going to have to be sized on a case-by-case basis, and you have to know a lot about that installation, that whole tracking down, logging, writing down all the cable lengths, cable types, even cable insulation is critical because it's dielectric constants, all this other stuff. Another way that we deal with them is we're going to go and deal with what's called a UPS type of system. A UPS means uninterruptible power supply. There's two main types of UPSs out there. They're going to be either online or offline. In fourth year, you're going to cover these things in depth. But the basic difference is that if I have got a UPS is designed to go and do, it's designed to go and feed through to my load. So almost the same as what we dealt with for transfer switches before, where we are going to go and have a transfer switch that's going to be inside of here. Here's my load. And then the UPS is going to go and maintain contact with my mains most of the time, and then it's going to go and have a charging system. Okay, so it's going to be a battery-driven system over here that's going to be charged off of that. It's going to have an inverter to come out of that. And so anytime that I lose power on my hydro end, then it would switch over to this, and it would go and deliver from that battery system out to my load itself. The two main types are going to be either the online, or I'm going to go and have the offline or the standby. The standby ones do have an interruption because power fails, they wait a little bit, then they go and transition right over to go and feed out my load. They are cheaper because they don't see continuous current flow. An online type actually goes and acts almost like a VFD, where I'm going to go and take this in, I'm going to go and convert it into DC. Let me see if I can draw that a little bit better. DC, and then I'm going to go and convert this thing back into synthetic AC on the output, and that DC is going to be fed out into a battery. And so that DC is just pulling out to, once again, here's all of my loads all at this end over here, but it's going directly through this. So it's always going to go and be online. If this would fail out here, once again, then the battery that I have, that's supposed to be a battery, we'll just make it more battery looking, will immediately go and come back on because it's always going to be connected to the system through that inverter as we head this thing back out. They are going to be more expensive for them to be online because they are going to go and have continuous current carrying capabilities. They're going to go and have, better controls. They're going to have a better inverter because it's always online, etc. And in some cases, they can actually go and create some poor, harmonics themselves. If there's a cheap UPS is worse than no UPS whatsoever. We'll oftentimes use these UPSs when we are dealing with emergency systems, particularly if you've got like critical data or hospitals or prisons or things like that, where you're going to go and have a UPS that's going to be coupled with your generator. So when we have got a fault, then hydro gets lost, the UPS provides the ride through just for a couple of minutes, at the tops. Usually it's just going to be a couple of seconds, while the generator comes up to speed, stabilizes, and we switch over to that generator. It's just designed to go and have a operation that would be upstream. So I'll use an online one over here. This would be what we would actually have for, I'll draw that one right there, and right there. This is going to be to my genset. This would be my incoming BC Hydro, like that, where we would normally be supplying power all the way through from BC Hydro. This would be my normal path all the way through. If then BC Hydro fails, that disappears, then in the meantime, this thing is going to, out of its battery bank, continue to go and run power out to the load. And while it's running power out to the load, the transfer switch is going to switch over to the generator picks up, and then the generator takes over from the batteries, and the batteries go back to charging up off of the system. Provides us with complete ride through itself. The generator and the generator transfer switch, they don't need to interface with the UPS other than that they're feeding power out. The generator is always going to go and be upstream of that UPS on our critical types of systems. Good quality UPSs are going to go and have a good set of reactors inside of them. In a lot of cases, they're going to go and have transformers as well that are also going to give us further filtering out of them. Line voltage regulators are going to go and regulate the amount of voltage that we are going to go and have. Some of them can regulate the power, but they can't condition it. In other words, they don't smooth it, but they are going to be able to go and adjust the amount of voltage that we're going to go and have out, particularly ones like the tap-trained switching transformer or the variable ratio transformer are going to go and change the voltage, but they don't really filter a lot. We do have some others like our saturable reactor, our resonant transformer, etc., that will provide some power quality fixes as well inside of there. They are going to be large, they're going to be expensive components, but they're going to be good for our over voltages and for our under voltages, right? That's what they're designed to do. They're not designed to go and take out any sort of harmonics. If I need to take out harmonics, then what I'm going to need to do is use reactors, as well as I'm going to have to go and use my zigzag rated transformers or my K-factor transformers. Talking about line reactors, they're the simplest and the lowest cost means of attenuating harmonics. It's simply going to go and be a coil that's going to be in line with my lines. We connect them in series with individual nonlinear loads. They're low cost, and they are going to go and give us, smoothing, because that inductor is what we refer to as a choke. They are going to go and use that magnetic field to deliver current anytime that our supply, is failing on that end. And they're also going to go and choke back any sort of these spikes that are going to be coming through either to our motors or coming back from motors, etc. They're also completely passive. You don't have to engineer these things. You just place them in line with it. They don't do anything unless there's actually a problem on there. And then it's all just through the electromagnetic interface that they have that they'll actually go and respond to these things. They are rated in impedances or %Zs that we're going to go and have. You want to pick a low impedance. It needs to be high enough it's going to be still significant, but low enough that it's not going to go and drop a lot of voltage before it gets through to your load. So about the 5% range is usually going to be suggested. K-factor transformers are going to be a type of transformer that does not go and cut out harmonics, but rather it can deal with them. It basically can just suffer through crappy harmonics. K-factor is just going to be the amount of overbuilding that that transformer has and the amount of crap that it can go and put up with, so to speak. It's going to be a constant based upon the build, right? We always use K to talk about constant based upon the physical components of them. When you go and do harmonic analysis, power factor, harmonics, etc., you're able to go and find out what's going to be K ratings. All of these meters are going to spit out K ratings, and if you have got a K rating that the system says, hey, look, you've got a K rating of 3, you got to match that with your transformer, that you are going to be able to then deal with that, because it's just telling you the size, or basically the scaling that we're going to go and have. Standard transformers have got a K factor of 1. So just a regular old isolation transformer is going to be considered to be K factor 1. Anything that is overbuilt is just going to be multiples of that. Isolation transformers. Isolation transformers are very commonly used just as part of our power distribution system. The beautiful thing is that they also provide a little bit of filtering that we are going to have on them. Our most common type that we are going to see of transformers is going to be where we are going to have that delta primary and that Y secondary, which inherently does deal with a little bit of filtering for us. Some harmonic attenuation that happens just off of that 30-degree phase shift that we are going to go and have. We also are not going to go and have triplet harmonics that are going to get trapped on there. They're just going to get dissipated. They don't pass through, but they don't get stuck inside of there as well to form like reflected wave systems or anything like that. We do need to go and make sure that we have got a low percent Z, the XL, that's going to be off of there. It's going to go and generate that percent Z. So we can pass our current at 60 hertz, but then it is going to go and increase once we go and increase our harmonic frequencies, right? XL is equal to 2 pi FL that we are going to have. So as our frequency goes up, our XL is also going to go up on both the primary coils as well as on the secondary coils. There is one other type of transformer that has got specialty windings that is going to go and have flux cancellations. Basically, we're going to go and get rid of harmonics because we're going to be able to go and push them against each other. We're going to use their own, harmonic frequencies to counteract each other. Usually, we're going to go and have a zigzag connected secondary with a delta connected primary, and we are going to go and have a phase shift. We know about phase shift from transformers at the beginning of the year that we've got standard, a 30-degree phase shift from A to neutral, as well as we're going to have another 30 degrees anytime that we go from a Y to a delta or a delta to a Y, etc. But we can go and change that phase shift through tuned types of windings that we are going to go and have. If we do have these types of harmonic mitigating transformers, they're going to go and still allow the harmonics to be generated, but they're going to go and make sure that they don't pass all the way through these. Harmonic filters are probably a better method than trying to go and size your transformers, because if you can take the harmonics out before they reach the transformer, you are then going to be able to, just not have to deal with it, right? We don't need to go K factor if we don't need the K because we don't have the harmonics that are going to be inside of there. All that a filter is it is going to be a circuit that is going to be tuned so that it can dissipate any sort of a frequency. If you go back to your second year where we dealt with series RLC circuits, we'll go and put an RLC circuit into ground here right now. Series RLC circuits are going to go and have frequencies, resonant frequencies that they're going to resonate at. And we know that when we hit a resonant frequency, the XL and the XC are both going to go and counteract each other, which are going to go and basically leave us with the lowest possible impedance, the Z, that's going to be left on there, which means that we can pass current through when it's the correct frequency. What we'll do is we will size these things, the actual inductor and the capacitor. We won't, but they'll be engineered to be sized so that at 60 hertz, there is going to be a fairly large Z. So if I were to take a look at my Z at 60 hertz, it's going to look, here, we'll actually draw it like that. At 60 hertz, my Z might look like that. But by the time that I take this thing up to 180 hertz, if I'm going to go and filter out, the third order, then what I'm going to see is that all that I'm going to really be left with is going to be a tiny little bit of Z and maybe a little tiny bit of, XL or XC that's going to be off of that. Therefore, it's going to have a very low Z. The actual physical resistance of the copper is the only thing that stays in there. And so it's going to go and dissipate those harmonic currents themselves. Really, really handy because we can tune them. Particularly if you go back to these over here, if you know what harmonic it is that you are really dealing with, if it's 180, maybe it's a 240, maybe it's one of your, 5th or 2nd or 7th or something like that as well. You can find that off of these graphs here, your largest one, and then you can just filter that one out specifically using those harmonic filters. Low pass harmonic filters are very, very cheap, very bulletproof, and very easy to go and apply. There's no actual amount of engineering that needs to be placed for these ones. What these ones have is they've got what we refer to in electronics as a low pass filter. We've got either low pass, high pass, or band pass, or we can have band stop type of filtering. But basically, if we take a look at frequency, we're going to go and have 0 over here that we are going to go and have. Not 0. That end will start over here with the 0 over here. What a low pass frequency will do is it is going to go and allow current. We usually analyze current on these things. Current through up until a certain point, and then all of a sudden it's going to go and bend down, relatively quick. We got like Bessel and Butterworth and Chebyshev and a bunch of other type of filtering methodologies that we can go and use off of it that are going to go and control what we call the roll-off here, basically the steepness of this graph. But what we can do is we can say that anything up to, if our 60 hertz is right over here, we're going to allow any lower values of frequency to go through, but anything past 60 is going to go and get attenuated. It's a decibel attenuation that we are going to go and have off of these. What you want to have is you want to have a low pass 60 hertz frequency, because if you're working with a VFD or anything like that, usually we're going to be changing our frequency anywhere from 0 all the way up to its rated amount of frequency. Occasionally we will go higher, take them all the way up to 90 or something, but we know that we'd lose torque when we start to go and do so. If we use a low pass filter, that means that any amount of current that through, from 0 to 60 hertz is going to pass through no problem. But as soon as we go past 60 hertz, this thing is going to start to clamp down. It's going to go and prevent us from passing that current through. So if I take one of these, if I got my drive over here, and then we'll go take our motor over here, what I can do is I can place one of these, a low pass filter, right here, right in front of it. And so anything that is going to be 60 hertz or less would be able to get reflected back out of here. But if I've got 180s, if I've got 120s, anything like that, this thing is going to go and dissipate off. They do need a connection to ground because they will have a resistance inside that they're going to go and burn off to ground through those frequencies. But it's going to be a passive type of filtering. It only becomes active when there is going to go and be that frequency that tries to bounce back out. You can place them on both sides of your VFDs. At that point, you'll be protecting your motor from a lot of your higher amounts of harmonics, etc. You're also going to be protecting the rest of the installation, because then you're not dealing with radiation coming off of these lines that would otherwise be out there acting like antennas. They're very cheap compared to a lot of our other fixes that we have out there. In some cases, they are going to go and be built into the drives themselves, that they're going to go and have a low pass filter. That's always a very good thing to see on a drive list over there. And they're just reliable. You don't need to go and do a lot of analysis. If you got, a place that has got a bunch of bad harmonics, and if you know that those harmonics all started up after you put in a bunch of motors, maybe you can go there, you can take a look around, but guaranteed that those motors and drives that you're looking at are where those things are coming off. So just throw these in off of the VFDs. Active harmonic filtering is a little bit different in that you've got CTs that are going to be placed on the system. And those CTs that are going to be placed on the system are going to be continuously monitoring and then switching in and out, either through saturable reactors, which are going to change XL, etc., or they're through variable inductance or capacitance methodologies that we have. You're going to be able to go and cancel out harmonics just by electronically going and running that in. But they are more expensive because they do need to go and have CTs that are going to be placed around the line. And then they are going to have, obviously, microcontrollers that are going to be consistently analyzing and changing. They also have to be incredibly fast, because you've got to remember that some of these frequencies, by the time we're out to the 30th harmonic, that's going to be 30 times 60. And so it's a wicked fast, we're getting up towards radio frequencies that we're trying to go and filter out. So it has to be able to quickly clamp down on these. They are expensive, but if it is a critical installation, they're worth it to go and put on there. But by far the most common ones that you are going to deal with is going to go and be the low-pass harmonic filters. They gave you a picture of one over here. It doesn't mean much to you guys inside of here, but this is going to be tuned so that it is going to go and pass. This section over here is going to pass anything greater than 60, and it's going to pass it directly down to ground. So any sort of crap harmonics are getting passed down to ground off of that. That's why we're showing 3 legs that are going to be off of that, and usually they're going to have a built-in resistance inside here as well to dissipate. Do remember that if you do have low-pass filtering, that those low-pass filters are designed to dissipate harmonics as heat. Okay, it's the safest way to go and do so, which means that you do need to make sure that they're going to be properly ventilated. All right, that covers it for Learning Task 3.